Okay. Good morning, everyone.
Morning.
Okay. Hi, today we are going to work with volume by shell. So it's going to be the whole hour. So let us remember what a shell is. So okay. A shell, as I told you yesterday, is basically like a can of pop, if you want. That's the way I saw you. So it took something like that. We have a little bit, the inside is totally hollow. And there is a certain thickness. That's a shell. And the height, it's long, it's not the height. That's a typical shell. And if I call this the radius, as I said, the radius, the outer and the inner are very close to each other. And this is the thickness. And from here to here is the height. Okay. And the volume of a shell, is almost equal. It's not equal, that's a real approximation of it. It's almost equal to 2 pi times the radius. And it doesn't matter whether you take the radius to the inner shell piece or the outer. That's why I have the approximation, because they are very, very close. Things in our scenario, the thickness is very, very small. It can be the delta x or the delta y. So it doesn't really matter which one you take, times the radius times the height times the thickness. Okay? That's the main idea. That's the main thing. So today we're going to start working with that. So we'll set up the problem and then we work with examples. So this is the setup. So we have, let R be the region. So R, the following region. So region bounded by the graph of y equal f of x, and the lines x equal to a and x equal to b. So rotate R about the y-axis, rotate the region R about the y-axis, and find the volume of the solid obtained. Solid obtained. So what we're going to do is the following. So we're going to have this region. That's my region. That's the region. And this is f of x. And f of x could be anything. Like, remember yesterday I gave like x cubed plus x squared. It can be any kind of complicated function. It doesn't really matter in this case. This is my a, and this is my b. And that's my region. And that's the region I need to rotate around the y-axis. That's the axis of rotation. We have to be always careful. What is my axis of rotation? Now, in the washer's method, when we rotated around the y-axis, we had to take those horizontal ones. And the issue was, if we take those horizontal slices, I need to solve for x in terms of y. And sometimes it's very hard. So we're going to avoid that by taking those slices, cover this region with those vertical slices. Okay, and as we did yesterday, you rotate it, you get the cylinder, and then you subdivide this into the whole region into rectangle, and you rotate every one of them. And you will get a cylinder inside the cylinder, and that's what's going to cover the volume. So we concentrate on a typical rectangle. And we rotate it. So this is parallel to that. So when we rotate it, That's what's gonna give us. In our mind, we really do the rotation. We're gonna get the cylinder when we rotate it. So the question is, what's the volume of the cylinder? So we're gonna rotate, typical rectangle, and I will here write, we're gonna rotate a typical, I'm gonna write a little bit more the first time, typical, thin, very thin, very vertical rectangle. This will give me a shell. So we have always to ask ourselves what type of shape we get when we rotate. Now, to find the volume of a shell, of a typical shell, we need the radius, we need the height, and we need the thickness. Once we identify each one of those items, we can find the volume of a shell. All right, so now the main idea. What is the radius of, we look at the picture very, very well. What's the radius of a shell? Now I'm asking you the question.
Is it xi?
Absolutely, xi, because where is the radius? We're rotating, this is the axis of rotation. So that's the center of the shell, because that's the axis of rotation. So my radius is gonna be from here all the way to here. That's the radius. Okay. Again, the picture is the best thing in all those problems. Once you can understand the picture, you're done. That's the radius. Now, what is my height?
F of xi.
F of xi, absolutely correct. That's the height. The height from here till you hit the curve. If the curve is f of x, that's the height. So f of xi. Finally, what's the thickness of the shell in this problem? What's the thickness?
Delta X.
That's the delta x. That's the delta x. As you realize, it's fairly simple, much simpler. When f of x is a complicated function, it's way simpler than having to solve for x in terms of y. I didn't have to do that in this case. X is my variable. I didn't have to solve for x in terms of y. I kept x the variable by taking those vertical rectangle, but in this case, they gave me a shell, not a washer. Remember, in the washer, the height is the delta x. So do not confuse those. In the washer, this height here is the delta x, which is not the case in my scenario. In my scenario, the height is f of xi in this particular setting. So volume of a shell now. Volume of a shell is almost equal to 2 pi times the radius times the height times the thickness. That's the volume of the shell. So the volume of the solid could be approximated by the sum of those shells. So now when I take the volume of the solid, it means I'm adding those little volume. I'm covering this. No, this is not the right one. I'm covering my region with those shells, the solid. I'm getting one plus the other, like the picture we saw yesterday, plus this, and we keep adding, and we keep adding. So it's the sum of the volume of the shell. It means the sum. And it depends, you take right, you take left, it doesn't really matter. So when n is becoming very large, it means when we take more and more subdivisions, this delta x will become a bit tinier and tinier and tinier. We are doing a better covering of the region. So when n become very, very small, this look like a Riemann sum, and that should become 2 pi x, f of x, dx, 2 pi times the radius times the height times the thickness That's how I read the inside of the integral. That's the volume of a shell. And when we integrate, it means we are adding those sums. Okay. So now we're going to sit down and start practicing this formula in a lot of scenarios.
I have a question.
Of course, go ahead.
Real quick, how'd you get the radius of xi?
Okay, very good. Let's go back to the picture. That's my only explanation in those problems. So I'm gonna redraw the picture for you to see it. This is my region. This is my A, and this is my B. Okay, and I'm gonna take my rectangle. This is my xi here, and this is the rectangle. Should be straight. Okay, what is the axis of rotation? The y-axis. We're gonna rotate this way, right? So imagine you're taking this here. Focus only on this line, not on the whole rectangle. Just focus on this line. And you rotate it around the y-axis. Focus only on this line. Are you with me?
Yes.
Only on this line. Rotate it. All right?
Yes.
The radius from where to where? Remember, that's the center of the cylinder. Sorry, I meant the shell. Where is the radius in my picture? From where to where?
Oh, it's a distance of xi, right?
Distance xi doesn't really make sense. It's the distance from where to where.
Oh, sorry about that.
That's okay. No, I want you to be precise so you understand it. You don't have to apologize. Okay.
You said the
distance from where to where?
Wouldn't it be the opposite side of xi? So wouldn't it be like a negative xi or something like that?
No.
Oh.
It's the radius on the picture. It's the horizontal distance from the y-axis.
Oh, from the y-axis to xi.
Right. This horizontal distance. You see it?
Yes.
That's the radius. That's my radius. So it's the xi value, whatever xi is. When I start splitting, the first radius will be to x0. The second radius will be to x1, x2, x3, x4, etc., etc. Is that clear?
Yes.
Very, very important. Okay.
Thank you.
Questions. All right. So now we're going to practice a lot of problems today. We're going to do a lot of problems. The first one is going to be a verbatim in application to that. And we proceed. So the first example is basically the reason we introduced the shell. So we're going to reproduce the thing. So suppose, very easy example. Suppose R, the region bounded by graph of y equal x to the power 3 plus 2x squared. The lines x equal to 1, x equal to 0. We're going to revolve about y-axis. And the question is find the value using the shell method, which will be the only way out. All right. So I will draw the picture in this scenario. X cube, we don't know how to draw it easily. So in case I give you x cube, I will definitely give you the graph. So it's going to look something like that. So that's x cube. That's the graph. X equal 1, x equal to 0. And let me add y equal to 0 to be very precise. Okay, so that's the graph. X equals 0, x equal to 1, and the y, the x-axis. So this is my region. And I'm going to rotate it around the y-axis. And the question is find the value. Okay, so let's remember something. If I take the washer, when we took the washer, we took those, we fixed the SI. I don't have to write this. I'm going to erase in a second. And we cover with those horizontal rectangle. To be able to do that, I need the inner and the outer. The inner would have been here. But to find the inner, I need to solve for x in terms of y, which is extremely hard in this particular scenario. So shell is really saving me from all this, because in the shell method, x is my variable. So I don't have to solve for x in terms of y. So now let us do it. I take my rectangle. This is my rectangle. And I'm going to rotate it around the y-axis. So this is my xi, as we did a minute ago, and we rotate it. So this is going to go like that. It's easy to basically draw the shell. Okay. At this stage, and then, of course, there is a certain thickness attached to it right there, which is coming because it's the whole thin rectangle I'm rotating. And now, actually, believe me, the problem is done. So rotate rectangle, vertical rectangle, give me a shell. The idea is I need the volume of a typical shell. So I need the radius, I need the height, and the thickness. So it's a verbatim application to what we did a minute ago. The radius, as I said, is from the axis of rotation till xi. So that's my radius, xi. Height. The height is basically from the x-axis till I hit the curve. That's the height. So the height is easy as well. It's the value of the function at xi. And this is my little delta x. So volume of a typical cylinder or a shell is almost equal to 2 pi radius, height, thickness. So we're adding little volumes. We're adding little volume. That's really the heart of what we are doing. We're adding little volumes that are covering the region. So the total volume is going to be 2 pi integral x cubed plus 2x squared dx. And in this particular case, to cover this region, I have to go from 0 to. Okay, the rest is simple. I usually do the first step in the integration process, and then I let you finish it. When it's very simple. The only way to do that is actually to distribute. Distributing will give me x4 plus 2x cubed dx. The rest, you should know how to do it. Okay? Questions as we move on.
You're finding the surface area essentially of the shell and then multiplying it by delta x.
This is the surface area.
Right.
Right. Delta x will do what to it?
We'll give it a thickness.
Right, it gives it the volume.
Okay.
Absolutely correct. That's the surface area. That's the volume.
Got it.
Okay, absolutely. Interestingly enough, we're going to use the same approach when we compute the surface area. So part 2 now, we're going to take another example. And so now example number 3, if you want. Whatever, I forgot. So R is the region, actually 3A, because I want to make this into 2 pieces. R, the region bounded by y equal x squared, y equal root x, and we're going to rotate about y-axis. Find the value. Okay. So graph. That's the only way we work in these sections. And y equal x squared y equal root x. Okay, and this point is 1, 1. And we want to do it using the shell method. That's my axis of rotation, the y-axis. Okay, so I'm going to exactly the same. So I'm going to fix my xi, and I'm going to take a cover it here with rectangle. So this is my little rectangle here. Okay, and I need to rotate this around the y-axis. Of course, we rotate this, we get the shell. The height is very large here. And if you don't draw a good picture, you're going to be totally confused between shell and washer and everything. Okay, my problem at this stage is done in the following way. So we need the volume of a shell. What's the radius? The height and the thickness. Okay, the radius. To find the radius, like we did for the disc and washer, we have to ask ourselves, what is the rotation? The rotation here in this example is still the y-axis. That's the rotation. So my radius is going to be, so when I'm rotating that from the y-axis, axis of rotation, till the bottom of the cylinder. So that's going to be my radius, which is exactly from here to here. That's the same length. So my radius is always my xi. What is my height? Quickly. As I set you up, guys, I'm going to start asking two questions. What is the height?
Is it xi squared minus square root of xi?
Right. It's the top value minus the lower value. Okay, so now this is the square root of x. This is x squared. So the height is always the top value, because basically that's the square root of xi here, and that's the xi squared. So it's the top minus the bottom. So again, back to top minus the bottom. Thickness is delta x. Volume of the washer is almost equal of a typical washer, 2 pi times the radius times the height times the thickness. And the total volume is, integral from 0 to 1, because this happened to be 1, it doesn't have to be, 2 pi x root x minus x squared dx. And as I said, I do the first step of the integration, and I let you do it when the easy part. The only way we're going to distribute here is we have to distribute. So x times square root of x. Now we know that integration doesn't like the square root, so we immediately have basically to turn this into x to the power a half to be able to integrate. And then I will have x times x to the half is x to the 3/2 minus x times x squared x cubed dx. And then you finish at this stage. Okay. Now B. I'm going to take the same region, but I'm going to change the axis of rotation. So I give you 2 minutes to interact with what I did.
Can you repeat what you just said?
What?
What were you looking for us to do?
Nothing. I'm just giving you time to take a breath. That's it.
Oh,
So
okay, gotcha.
that's it. B.
Cool.
Okay. The question is the same region as before, but I'm going to rate, so same region as above, but revolve, and I rotate it about, I'm going to change the axis of rotation, x equal to 1. So it's always parallel to the y-axis, but I'm going to change the axis of rotation. And we're going to find the volume. Okay, so I draw the picture. As you realize, there is no memory at all assigned to those ideas. So now this is my region, the root x, the x squared, and the intersection was at 1, 1. So x equal to 1 would be exactly this line. That's the axis of rotation. And I want to do the exact same thing. I want to rotate this around the axis of rotation. So around, sorry, the line x equal to 1. So I'm going to take my thin rectangle here. Okay. I'm going to take, this is my xi down here. And I'm going to rotate. Remember the axis of rotation, this is the axis of rotation. You have always be careful with your axis of rotation. All right, so we get the shell. And now we have to find the volume of the shell. So to find the volume of the shell, we need the 3 things. We need the radius of the shell. We need the height of the shell. And finally, we need the thickness of the shell. All right. What is the height? Sorry, what's the radius? What's the height? What's the thickness? I give you a minute to tell me what the radius is.
1 minus xi.
Absolutely correct. Let's see what the radius is. It's from where to where? The picture's changed tiny bit. So it's from the base of your rectangle to your axis of rotation. So this is the radius now. That's my radius. So it is the radius. So what's the radius? The value, if you want at the right value minus the left value. Or it's the 1 minus the xi. The right value is 1, the left is xi. So the radius is 1 minus xi. The rest is verbatim the same. There is nothing into the problem. It's only the radius that's changed in this scenario. I'm only changing the radius. So my height is the square root of xi minus xi squared. My thickness is the delta x. So this is my height here. Okay. So volume of a shell is almost equal to 2 pi 1 minus xi square root of xi minus xi squared, 2 pi radius height times the thickness, which is delta x. So the total volume will be the integral from 0 to 1 of 1 minus x times the square root of x dx. And the only way to integrate this problem, y 0.5 to 1. To cover the region, I have to divide the interval from 0 to 1. Now, you cannot shift because that's where the regions start. And now the only way to integrate this is you have to distribute. There is no way out. You distribute, then you will have very easy expression and we evaluate the integral. I'm going to take the same region. I'm not moving away. And then I'm going to change again the axis of rotation. And then we're going to move to rotation around the x-axis using the shell method. So just to make sure all of you get this very well, it's actually, I don't think it's hard. So C would be same region. But let us revolve about x equal -1, for example, just out of practice. Okay. Are you guys done with this page? Can I move on?
Yeah.
I need your help. All right.
Yes.
Yeah, you have to tell me yes. Otherwise, if you don't answer, I will move it, and some of you aren't done. So let us see. It's the same region. I'm not really changing my region. I am only changing my axis of rotation. And you have to tell me quickly how the picture will change. So this was square root of x. This is my x squared. This is -1. And this is my axis of rotation. So we're rotating about this. Okay. So, all right. So we have to take the shell. I mean, there is no really way out. So this is my thin slice. This is my xi. And I'm gonna rotate. So rotate. So this is the center of rotation. So it's just gonna go a little bit farther away. Okay. Right. So again, we're getting this nice shell. And to finish the problem, we mainly have to figure out the little pieces of the shell. Okay. All right. And okay, the height hasn't changed. That's the height. So the height is the upper curve minus the lower curve. The thickness haven't changed. It's the little delta x. It's the radius that we have to basically figure it out. So again, this time I'm going to ask one of you because I want to make sure all of you are with me. Let me pick one. I don't know. Matthew, are you with me?
Wouldn't it be xi minus -1 or something like that?
Xi?
Yeah, xi +1.
Absolutely correct. Okay, you can do this two ways. Either you look at the picture, look at it. The radius is from where to where? From here to here. It means from here to here. That's the radius. So if you look at the picture, this is xi, this is 1, pure and simple. Or if you forget, whenever you have 2 points on a horizontal line, the distance between them is the right value, which is the xi, minus the left value, which is xi plus 1. End of the problem, basically. So the total volume is going to be the integral from 0 to 1 of 2 pi radius, height, thickness. My problem is done. Now it's just a matter of integration. Okay. So let me, I'm going to do one more problem in the following way. We used the shell so far when we have rotation around the y-axis or a line parallel to the y-axis. We can also use the shell when we rotate around the x-axis. So I'm going to take example where we're going to use the shell when we have a rotation around the y-axis. Okay, so this is the problem. And then we're going to contrast shell and washer, so to help you fully not confuse them. So my problem is the following. So cylindrical shell could be used to rotate around y-axis. So use
The
shell
upper and
method.
lower bounds for that previous problem Shouldn't it be -1 to 1?
Good question. Answer your question. This is a typical confusion among students. I want you to be able to resolve it. When we found the bound, what's the question we ask ourselves? Do you remember? Anybody? I mean, I'm asking everybody. When we decide to find the bound, what question do we ask ourselves? Because his question is very good. I have a lot of confusion with that.
It's what area are we dividing into rectangles?
Exactly. Which region or which interval we have to divide to cover the region. That's my region. Are you with me?
Yes, got it. Thank you.
Exactly. Which interval? This one. If you go from -1 to 1, it means you're dividing this, but then I don't know what you're doing anymore.
Right.
Is that clear? Very good question, because this causes a lot of confusion among students. What are the bounds? All right. So now the question is, use the shell method to find the following. To compute, I mean, I'm going to put in an easy scenario to compute the volume of the region of the solid obtained by rotating the following region. Let's see how I'm going to put it. Okay, I'm going to put it in this way. X equal 9 minus y squared in first quadrant. Y equal to 0. X equal to 0 about the x-axis. Okay, the value obtained by arc. All right, so let me draw. I will draw the picture for you. I draw everything. So this is my region. Okay. X equal to 0 is this line. Y equal to 0, I mean the other way around. Y equal to 0, X equal to 0, and the shell was so in the first quadrant. In the first quadrant. Okay, bounded by that. Now x equal 9 minus x squared. Let me talk a little bit, how do we graph it? So if I want to graph x equal 9 minus y squared. Okay, the one that you should know is x equal y squared. So x equal y squared is this graph. All right? So x equal minus y squared basically should be this one. It's just like that's x equal minus y squared. Okay. If you want x equal 9 minus y squared, you take this graph and you push it right here. And then you get this picture. So that would be x equal 9 minus y squared. It's like what you do when y is given as a function of x. So if you had y equal x squared, that's the graph. Y equal minus x squared, that's the graph. And y equal minus x squared plus 9, you shift up. Now you do everything, but with respect to the x-axis. So x equal 9 minus x squared is going to be something like that. Basically, it should keep going, but I want the first quadrant, so I'm not interested in the bottom part. So that's really my region, this one. This is x. I'm giving to x in terms of y. I didn't have to, but to make the problem slightly easier. This point here is what? What are those 2 points? Right here, y is 0, so x is 9. That's 9. Right here, x is 0, right? If x is 0, it means y equal to 3. Okay, those are those 2 points. And I'm going to rotate it around the x-axis. Right? So that's region. So we get something, you know, this is not hard to imagine. We get something like that. And the question is to find the volume. Now, what type in the cylindrical shell? How do we take the cylindrical shell? How do we take our slices? Our slices are taken basically parallel to the axis of rotation. If we take,
Horizontal.
right, if I take vertical slices in this case, and I rotate them, I'm gonna get a disc, not a shell. So in a shell, and this is, I'm going to write in big letters later on, my slices are parallel to the axis of rotation. That's how I get a shell. Otherwise, I won't get a shell. So now I'm gonna fix my yi. So my yi is my variable. And this is the shell. This is the piece I'm going to rotate. Okay, so I'm gonna rotate that. Rotate this, rotate. And this is the shell I'm gonna get. So in the shell method, to help you memorize it, the slices are always parallel to the axis of rotation. That's how I get a shell. If they are perpendicular, we actually do not get a shell. Now, basically, I am almost there. I want you to stay focused with me on the little pieces, not the little pieces. So this is my shell as you see it. I need my radius. I need my height. And I need my thickness. So not in this case, because I'm taking those horizontal slices, y is the variable. Always ask yourself, what is the variable? So here, y is the variable. So everything has to be in terms of y because I need to divide the interval on the y-axis. Okay, so now back to you. What is the radius in this scenario? All of you are responsible.
Y.
Right?
YI.
Absolutely, yi. Because the radius is from the base to the axis of rotation. That's the radius. Okay, that's my radius. So my radius now is the yi. Okay, that's the radius. So it's from the base of the rectangle you have till the axis of rotation. That's really my radius. My height, that's my height from here to here. So if I have the yi, the height is the x values, the horizontal distance. So it's the x that correspond to this yi. In this particular problem, I give you x in terms of y. I don't have to do that. I can give you y in terms of x, but then you have to solve. So I don't have to give you this. So the height, it means that how do you read this equation? This equation tells you if I know the y, I know the y. This tells you the x distance till you hit the graph. So the height here is the 9 minus yi squared. The thickness is a little delta y. Delta y. So volume of a typical shell is almost equal to the following. 2 pi times the radius times the height times the thickness. Yeah, the answer is yes to Fred. Yeah. Where am I? So the total volume is the integral of, so we're adding those little volumes, dy. And then the question is the boundary. Now I go back to my region. That's the region. And the idea is to cover this region with those slices. So the interval I have to divide is the interval on the y-axis, is the interval from 0 all the way to 3.
Is it 9 minus y squared or 9 minus y?
What did I write? Oh no, absolutely y squared. No, I'm not going to change anything. I'm not gonna do this problem writing, but I'm gonna ask you the questions. If I, okay, this is my question. If I take the same region, I don't change anything except the axis of rotation. So suppose I take the axis of rotation here. So the same thing. I don't want to do the whole setup. That's the region. And I change my axis of rotation. Suppose I make my axis of rotation the line y equal -1. So this is my thing. This is my little piece. And that's the one I'm going to rotate. What will change in this picture?
Radius.
Radius.
The radius. What's going to be the
Radius.
radius in this picture? As I said, I will not redo the whole problem because I think I've done enough. What's the radius in this picture? Let me pick it. Go ahead.
yi plus 1.
Yi plus 1. That's the only thing that changed. Or if you want, the higher value minus the lower value, which is yi plus 1. Because whenever you have 2 points on a horizontal, the distance between them is the upper value minus the lower value, the top minus the bottom. Okay, and then you know once you know the picture, I can put my axis of rotation actually anywhere you want. Like here, it doesn't really matter. So if I put this 4, the radius should be 4 minus YR. So we can now play with the axis of rotation. There is no issue with that whatsoever. So now, just as a sum up between washer and shell, to help you focus a little bit, In the shell method, the slices are always parallel to the axis of rotation. This is when they generate a shell. And in the disc / washer, the slices are perpendicular to the axis of rotation. So this little remark basically will help you a little bit. Okay. And which is the variable, it actually, you should look at the problem. Okay, did you take vertical slices or horizontal? And that's what tell you what the variable is about. So disc versus the shell, which method you use? All right. One place you use the shell method immediately, if you have, let us say, as I started the lectures, when I had a hard function, so supposedly I had a hard function here. This is y equal, actually any function. If you have any function here, whatever I had, in this scenario, the shell is much easier because you just have to do that times x, f of x. So this is much easier than the washer, unless I tell you do both, which I usually make you do both just to learn better. Now, another scenario I'm going to put on the board, on the paper, and the question is, which method you prefer and why? So question is, which method you prefer and why? Here's my problem. Let R be the region. Bounded by y equal or 1 over x, very simple region, very, very simple region. X equal to 1, x equal to 2. And revolve about y-axis. And my question is going to be, which method is better and why? It's not like tell me this is better, but you have to tell me why it is the better choice. And what's the problem with the other one? So y equal 1 over x. That's why y equal 1 over x. This is x equal to 1. is x equal to 2. Okay. So you have to tell me shell versus washer. And this is the axis of rotation. And the function is very easy. So that is really not an issue with the function. Y is 1 over x. It means x is 1 over y. So solving is not an issue. So now back to you. I'll give you a minute to think about it because you need to think about it. And tell me which is easier or what's the problem with the other approach.
It would be a lot easier to do the shell method with this problem.
The shell method? Is it easy?
I was gonna say to this method, do this last washer.
Okay.
We could do that, but then we would have two different height, like two different equations for the height we would have to use.
If you do shell, you don't have to change the function to be in terms of y.
But is it a hard function to change?
I mean, it's not necessarily hard, but it still makes it simpler to use shell, I think.
Okay, so let's use the shell. But I want you to tell me actually a different reason why the washer is problematic. So let's use the shell. If I use the shell, the radius is going to be the x, very easy, xi. The height is 1 over xi. The thickness is delta x. So the volume is going to be from 1 to 2 this time. 2 pi. Of course, this is the much simpler. I mean, this is really trivial, basically. Okay, which is basically nothing more than 2 pi integral from 1 to 2 to dx. So way simpler. Whatever. You finish. Very good. What's the issue with the washer? It's not that, because that's easy.
If you did the washer, would you have to split it into two different integrals?
Here you are. That's the problem with the washer. We have to split into two integrals. Why do we have to split? Watch carefully the picture. Carefully. If I use the washer, I need slices. These are the slices that I need to wash. These are the slices. And watch carefully the problem with your slices. I can take a slice here or the slice here. Right? If I take the slice, the down slice, the one right there, what's going to be the inner radius? Remember, I'm getting washers here because there is this big hole. So if the slice is here, what's the inner? What's the outer? Back to you.
Inner would be 1 and outer would be 2.
Very good. If I take, so this is my yi now. If I take this slice, what's going to be the inner?
The inner would be 1.
What's going to be the outer?
1 over x.
Absolute. No.
1 over y.
Yeah, y. What's my variable here?
Y.
Y. So it's going to be 1 over y. So if I have to do the washer here, I have basically to have a line and to consider two regions because my slices is absolutely changing in this scenario. So you have to be always, I said, you look at the picture, so you understand verbatim here. So if this is 2, this has to be a half because that's the graph of y equal 1 over x. So it's going to be a half. And if this is 1, this is going to be 1. So now I have to split. So if I use the washer, and that's really the main issue here with the washer, it's not solving because solving is not really hard. It's really so if you have to use the washer, and then I have to split my problem between, so this is my 1, so this is 0, and if y between 0 and a half, the inner radius is 1, the outer radius is 2. However, If my y is between 1/2 and 1, so my yi happen to be here. This is my inner radius, which is 1, and the outer radius is from here till I hit the curve. That's this horizontal distance. And this is 1 over the yi. Okay? So the inner is 1, the outer is 1 over yi. So the whole volume will have to split. From 0 to 1/2, I have to split. I have no way out. 1/2 to 1. Pi times the outer radius minus the inner radius, the gy. Sorry. 2 pi, pi times the outer radius minus the inner radius. Okay, so that's really the issue. If we use the washer in this problem, we actually not only we have to solve, but also there is a deeper issue, is the idea of splitting into region. All right. Okay. I definitely stop. Please do this. Your quiz will cover everything. It means your quiz, I think we did enough with the washer. Your quiz will cover disk, washer, and shell for tomorrow. Please do the homework. It's already, it will be at 9 o'clock on MATLAB. Please do it for tomorrow. Do not slack, do not fall behind. Any question before I let you go?
Is there any other review we can do on top of the homework?
More homework. Just pick any problem you want from the book and you will be okay.
Okay.
All right. Pick any other problems, that any odd problems, and do it and check your answer. All right.
All
If
right.
you have difficulty, let me know.
All right. Cool. Thank you.
Sure. Bye-bye, guys.